So it has been a long time since the last video. I was quite busy for the past couple of weeks, but yep, here I am. I'm gonna continue where I left off. So in the previous video, I basically discussed the proof of the nested interval theorem with the intent to use that theorem and some additional lemmas to prove the Bolzano-Weierstrass theorem. And the eventual purpose is to write a proof for the extreme value theorem. Okay, so there are three additional lemmas that we need to look at before we can write a proof for the Bolzano-Weierstrass theorem, although some would argue that they are essentially only two. So the first of those is the fact that every bounded sequence in the real numbers has a convergent subsequence. The second one is the same theorem except in r to the power of n. So every bounded sequence in r to the power of n has a convergent subsequence. And for those of you who know about completeness, it's actually the second definition that we use to basically define completeness in r to the power of n. Okay. And then the third one is, it says let S be a subset of r to the power of n and x be a vector in r to the power of n. And then x is in the closure of S if and only if there exists a sequence S which converges to x. So just to quickly clarify what it means for x to be in the closure of S. So I'm gonna just assume that we're in R2 right now. And let us assume that this is the set S. So it's a rectangle in r to the power of 2. So x is in the closure of S if and only if it's either on the boundary of S or somewhere inside S. So that is basically what the closure of S refers to. Okay. So yeah, that's one thing. And what I would also like to emphasize on is that I'm actually not going to write a proof for the second one. The second one over here, the second theorem, it's essentially the proof of the second theorem is essentially the same as the first theorem with a little bit, I mean, you essentially end up using the first theorem as a lemma in order to prove the second theorem, but I'm just going to leave that as an exercise for you guys to try on your own. Just be careful, there's one trick that you can fall into very easily when you're trying to prove the second theorem. So yeah, it's not as easy as it looks. Okay, so let's begin. So I'm going to start with the first theorem and then I'm going to prove the second theorem in this video, and then the next video I'm going to finally write out the proof of the Bolzano-Weierstrass theorem. Okay, so let's begin with the proof of the first theorem. It says that every bounded sequence in R has a convergent subsequence. Okay, so first of all, what is the idea? Exactly how am I going to go about proving this theorem? So first of all, notice that since by assumption the sequence is bounded, it must have a supremum and it must have an infimum, right? There has to be a largest value of the sequence and there has to be the smallest value of the sequence. Or in other words, you can say that there is one value which is larger than all terms of the sequence, and then there is one value that is smaller than all other values of the sequence. So I'm just going to say that those are A and B. So A is the smallest and B is the largest. Now this is where I'm essentially just going to end up using the nested interval theorem. So what I'm going to do is I'm going to divide this into two parts. I'm going to say that one of these parts must have infinitely many terms of the sequence, and let's say that is this part. I'm going to say, okay, let's just call this I1. Now divide this I1 further into two parts. There has to be one part with infinitely many terms, and let's say that this is this part, and I'm going to label this I2, and I'm going to continue doing this. I'm going to eventually say that by the nested interval theorem there is only one point that lies in all of these intervals, and then I'm going to prove that there exists a sequence, so a sequence of real numbers in this case, that converges to that point, so the point that lies in all the intervals. So that is the idea of the proof. Let's go about and let's start proving this. So first thing I'm going to note, let A of n, which is a sequence of n, be a bounded sequence or let's say be any bounded sequence, in R. That is, there exists real number a and b in the set of real numbers such that a is less than or equal, such that for every n in the set of natural numbers, a is less than or equal to a of n, which is less than or equal to b. Next, consider the interval a comma b. So the closed interval a comma b. And this is where I am going to create those intervals that I was talking about. So what I'm going to say is or let's say constructing, let's just label this something. I'm going to say constructing the sequence, or constructing the subsequence. Okay, so let's begin. So what I'm going to say is let I of 0 be equal to the closed interval of a comma b. Next, I'll bisect I of 0 into two equal parts. Notice that at least one of these two parts must contain an infinite number of terms of the sequence a of n. Let this interval be I of 1. Note that I of 0 is a superset, or it's a superset of I1. Okay. Moreover, continue this process inductively that is, given an I of n, in order to obtain I of n plus 1, I'll bisect I of n into two equal parts and pick the part with an infinite number of terms of the sequence S of n, and call it I of n plus 1. So this is the interval This is how I'm creating the intervals. There are two things to note that ice of 0 is a superset of ice of 1, which is a superset of ice of 2, and this continues indefinitely. Also, the other thing you need to notice is that the length of the interval shrinks, the length of these intervals shrinks to 0 as n approaches infinity. So how do you prove that? I mean, you can basically just go ahead and say what the length of each interval is. It's just p minus a divided by 2 to the power of n, and then as n approaches infinity, that goes to 0. But I'm just gonna, for now, I'm just gonna leave it this way. I'm just gonna say as n tends to infinity, ice of n tends to 0. Then, by the nested interval theorem, there is exactly one point which lies in all ice of n's. Or in, yeah, well, okay, yeah, I guess that's fine. I'm gonna leave it this way. So now there's exactly one point that lies in all of these intervals. In fact, you know what, I'm just gonna write it out as in all of these intervals. In all of these intervals. If you want to be a little bit more rigorous, you can say that there exists a unique L in the set of real numbers such that while L is in the intersection of I equals 1 to infinity of all of these intervals of I suffice. There you go. Okay. Let this point be L. Okay. Next, I have to define a sequence now, because this was a sequence of intervals. What I want is a sequence of real numbers. So the way I'm going to do this, I'm going to say next I pick or next I'll construct, or I'll define a subsequence of a of n as follows. So here's how it's going to work. So a of 0 is basically just anything that is in I of 0, okay, and then a of 1 is an element in I of 1, and this process continues indefinitely, where a of n, where for every n in the set of natural numbers, a of n is an element of I of n. So lastly, so this is how I have constructed my subsequence, and I guess the better way to label this is as follows. I'm just going to relabel this real quick. Actually, the only part I have to relabel is this very last part. Instead of doing it that way, I have another idea. What I'm just going to say is let b of j, which is a sequence defined on j, be a subsequence of a of n such that a of 0 is in I of 0, b of 0 is in I of 0, b of 1 is in I of 1, and then for every j in the set of natural numbers, b of j is in I of j. Now, the very important thing to note at this point is that this is always possible to do, because in each one of these intervals, I of 0, I of 1, I of 1, I of 2, and so on, as long as j is finite, I have an infinite number of terms of the sequence a of n. So it is always possible to pick a particular number that lies in that particular interval. So given that, now I can basically just complete my proof. So I'm going to say finally, I'll show that as that as j tends to infinity, b of n tends to 0. B of n tends to L. Now, there are several different ways to do this. You can go about and write out the rigorous definition of what it means for a sequence to converge and then prove it rigorously. I'm not going to do that. I'm just going to give you a basic idea about how the proof is going to go. It's generally sufficient. So I'm going to say note that as j tends to infinity, the length of the interval I of j, so this implies that the length of the interval I of j tends to, or well, I will just put a comma, actually length of I of j tends to 0, but notice that the length of I of j is less than or equal to the distance between b of j and L. Now, why is that? Let's say that the sequence or the interval I of j is this interval. So what is the maximum difference or the maximum distance between b of j and L? Well, first of all, we know that L has to lie inside I of j, so it can either be an endpoint or it can be somewhere in between. If it's somewhere in between, then no matter where b of n lies, it will always, its distance from L will always be less than the distance or the length of I of j, because b of n also has to be inside I of j. So if it's here, this is the distance between b of j and L, whereas this is the length of the interval I of j. So the greatest distance, of course, will occur when L is right here and when b of j is right here. And in this case, of course, the length of I of j and the length of b and the distance between b of j and L are equal. So what I'm going to say is, this implies, so if the length is tends to 0, and because of the fact that the distance between b of j and L is always less than I of j, it also implies that the distance between b of j and and L will also tend to 0 as j approaches infinity. So this implies that that b of j minus L tends to 0, and of course this implies that b of j tends to L as j approaches infinity, and that completes the proof. So this is really why we needed the nested interval theorem. There are different ways to prove this. You can also use the monotone convergence theorem to prove this, but I just like this. I just like it better to prove this theorem using the nested interval theorem. I just find it a little bit more intuitive, and in fact, I mean, this argument can actually be made entirely geometrically without doing any algebra at all. So I just find this proof, or the proof of this theorem using the nested interval theorem, to be a little bit more elegant. But of course, you can go ahead and use the monotone convergence theorem, and there are also other ways to prove it. So yep, that's the first proof. The first proof, that is, every bounded sequence in R has a convergent subsequence. Now I'm just going to give you a little bit of a hint for part 2. I'm not going to prove it, and then I'm just going to quickly write out the proof of part 3, or the third theorem, which is very, very small. So for the second one, I just want to, the hint that I want to give is basically a mistake that a lot of students make. So, I mean, let's see what a sequence in R to the power of n looks like. So if you have a sequence in R to the power of n, you can essentially define it something like this: A of n, B of n, C of n, D of n, and let's say I'm also going to go, okay, well, I guess this makes the point. So I have these 4 sequences. Now, the important thing to note is that all of these 4 sequences, as of right now, can diverge, and that's absolutely fine, because what we need to prove is that there exists a subsequence of, let's label this x of n. So let's say this is the sequence x of n, and what we need to show is that there exists a subsequence of x of n that converges. So as of right now, let's say A of n diverges, B of n diverges, C of n diverges, and D of n also diverges. But we need but the sequence is bounded. So what we need to prove is that each one of these sequences must converge, or there exists a subsequence of x of n that converges. Now this is the mistake here's what the mistake is that a lot of students make. So what they do is they say, well, okay, we've already proved this for in R. And since the sequence is bounded, we know A sub n is bounded, B sub n is bounded, C sub n is bounded, and D sub n is bounded. Thus, we know that there exists a subsequence of A sub n that converges. Let's label that A prime of j. And same thing with B prime of j, same thing with C, and same thing with D. And this is incorrect. So why is this incorrect? Here's why it's incorrect. Because the issue is, generally when you write out the proof, this is not the notation you use. The notation you use is, you define it something like this. So it's a subsequence of A sub n. So we generally label that as A sub n of j, and we start at j. So it's what we are trying to emphasize over here is that this is a subsequence of A sub n, and it is not dependent on n, it is actually dependent on j, where n subscript j is a bijection on the set of natural numbers. So that is how we generally define a subsequence. We don't use this prime notation or something like that. I just didn't want to confuse you here, which is why I just said let B sub j be a sequence of A sub n, a subsequence of A sub n. But this is still incorrect, and the reason why it is incorrect is because all of these are dependent upon j as of right now. And there's a fundamental issue that's going to occur, and the issue is that, let's say that j defines a subsequence of A sub n that converges. It is not, not a given. It's not true that it also that the same, interval or the same subsequence or the same order in which you're adding up the terms, or the same terms that you're eliminating for a particular sequence will also ensure that B sub n, for example, converges. So A sub j can be a subsequence of A sub n that converges, while B sub j can be a subsequence of B sub n that diverges. So there is no guarantee that they all will converge for the same subscript, and this is the loophole or not the loophole, this is the mistake that a lot of students make. So how do you go about this? The idea is simple, although if you don't know this other theorem, you should probably go about proving it first. And the theorem is, it says that if a convergent sequence, if there is a sequence that converges to L, then every subsequence of that sequence will also converge to L. That is the idea that you have to use before you begin a proof in R to the power of n. But once you know this theorem, it's actually pretty easy. Let's say that A sub j is a subsequence of A sub n that converges. We label that A sub j for now. Okay, so we know that A sub j converges. The next thing what I'm going to do is I'm going to say, well, let B sub k be a subsequence of B that converges. So let's say that this is B sub k. But now I'm going to come back and I'm going to change this to A sub j sub k. Now A sub j sub k is a subsequence of A sub j, where A sub j is a subsequence of A sub n. We know that A sub n diverges, but A sub j is a subsequence of A sub n that converges. And since A sub k is a subsequence of A sub j, we know that A sub j sub k also converges to the same value as A sub j. And then you can continue this process. So you can label C to be, let's say C sub I. Then you just go back and change all of these to I, and then you do the same thing with D sub j. You now define it as j. So now this works. Okay, not j. I've already used j. Something else. Let's use S, and now this works. So you can actually go ahead and prove this now that if you made all the assumptions correctly, this is a sequence that converges, and this is now a sequence. This is a subsequence of x of n, and it's defined as S, and you can prove that this converges. So yeah, that's basically the idea behind the second theorem. I'm not going to prove it because it's a straightforward proof. The major idea is this one right here, that for the major theorem, or the major idea that I'll be using later on for the Bolzano-Weierstrass theorem, it is the idea behind the proof that every bounded sequence in R has a convergent subsequence. Although for the Bolzano-Weierstrass theorem, I will use the second theorem as well. I'll just assume that that is true, and I'll leave the proof to you guys. So let's just quickly do number 3 and then we're done. So number 3 is a pretty straightforward proof. It says let S be a subset of R to the power of n and X be an element in R to the power of n. I want to show that X is in the closure of S if and only if there exists a sequence in S which converges to X. Okay. So this is the proof for part 3. And you'll see that this is actually a straightforward proof. It's not complicated at all. So I'm going to say that S be a subset of R to the power of n, and let X be an element of R to the power of n. And of course, I want to show that the vector X is in the closure of S if and only if there exists a sequence A's of n in S such that as n tends to infinity, A's of n tends to X. Okay, so of course there are two directions to prove. The first thing I'm going to do is I'm going to prove the forward direction. I'm going to prove this implication. So let's assume the vector S is in this. Okay, it's in the closure of S. So if it's in the closure of S, there are two possibilities. Either it is in the interior or it is on the boundary. So I'm going to deal with the case where it's in the interior first. So case number one is X is in S interior. In this case, it's very simple. Pick A's of n to be equal to vector X for every n in the set of natural numbers. Then as n tends to infinity, A's of n tends to X, which is, I mean, of course, the case because A's of n is always X. So this is the easier case. The harder one is when X, or it's not really hard, it's just harder than this one. It's X is in the boundary of S. Now, if this is the case, now you have to be a little bit careful because I've seen some students, what they do is that they still make the same argument. They say pick A's of n to be equal to the vector X, and then they run the same argument. But it's actually not true because we have never assumed in this entire proof that S was a closed subset of R to the power of n. Because if it was closed, then it is true that the boundary of S is an element or is a subset of S. But it might be the case that the boundary of S is not the subset of S in this case, because if the set is open, or I mean, if the set is not closed, I guess that is the more precise term, then the boundary of S is not a subset of S. So with that in mind, exactly what we are going to do, it's actually quite simple. Now, if X is in the boundary of S, this actually means something, and there's a rigorous definition for it, and the rigorous definition says that for every epsilon greater than 0, this you have to be a little bit careful. The ball centered at X, comma epsilon, intersection with S is not empty. And it's also true that the ball centered at X with radius epsilon, intersection with S complement is not empty, but we're not going to use the second fact. But both of these have to be true in order for X to be in the boundary of S. So here's what I'm going to do. Here's how I'm going to define my sequence A's of n. So I'm gonna use 1 over n. I use epsilon equals to 1 over n, where n is a natural number, where n is some natural number, in, let's label this 1, in 1. Then I know that the ball centered at vector X, comma 1 over n, intersection with S is not equal to the empty set, and I know that the ball centered at X, comma 1 over n, intersection with S complement is not equal to the empty set. Now here's the idea. Here's I'm going to construct the sequence, and I mean, this is basically the idea behind the entire proof. So defining A's of n. Okay, so this is how it's going to work, and what I'm going to say is, for A's of 1, pick any A's, pick any I'm gonna say pick any point in S such that or I guess this is not the right way to write it out. What I'm gonna say is let A's of 1 be a point be a point in S such that a sub 1 minus 1 in absolute value, or hold on, let me just see this real quick. Yep, vector a sub n, a sub 1 actually. So essentially what I'm thinking over here is that vector x minus I mean what this part over here, what this is essentially saying is that if you have a ball centered at vector x of radius 1 over n, then there are always elements of S that lie in that ball. And what I'm saying is that pick a sub 1 that lies in that ball. So yeah, I don't know why I messed this up. So it should just be pick a point, let a sub 1 be a point in S such that a sub 1 is an element of the ball centered at vector x comma 1 in this case, because it's a sub 1. And then we're going to continue this process inductively, and we're going to say let a sub n be a point in S such that a sub n is an element of the ball centered at vector x comma 1 over n. Then by construction, the sequence a sub n of n lies in S. Okay, so moreover, for every n in the set of natural numbers, a sub n, it lies inside the ball centered at x with radius 1 over n. And of course, this implies that the distance between vector x and a sub n, which is also a vector, is at most 1 over n. Why is this true? I'll just give you a little bit of an idea. I'm just gonna let's draw a ball in R2. So there you go. And we know that this is centered at x of n and its radius is 1 over n. Then as a sub n lies somewhere inside this ball, it must be the case that the distance between x of n and a sub n is at most 1 over n. So yeah, there you go. So thus, and we're done now, thus, as n tends to infinity, x negative a sub n tends to 0, or while it's less than or equal to 0. And of course, because it's an absolute value, this implies that it's equal to 0. It can never be less than 0. Or in fact, I should use tends to 0. And this implies that vector x, by the way, I should yeah, I just prefer it this way. Vector x tends to a sub n, and or sorry, a sub n tends to vector x, and that's it. We're done. So this is the idea behind the proof. This is of course the first part of the proof, but it's very important to understand why this works in order to figure out how it works in the opposite direction, because the other direction is actually in my opinion a little bit harder. So I mean, there are two cases to this. The first one is if x is in S interior, which is quite simple. You just pick the sequence to be x for every n that is in the set of natural numbers. And if vector x is on the boundary of S, what you need to do is you need to pick a sequence of the way you define the sequence is by using the fact that any ball centered at vector x with any radius is intersection with S is non-empty. Yeah, and basically what you do is you say, well, okay, the first thing I'm going to do is I'm going to pick a ball centered at vector x with radius 1, and I'm going to pick a term of my sequence in this ball. Then I'm going to keep on decreasing that radius of that ball. So 1/2, 1/3, 1/4, 1/5, and on each step I'm also going to pick a sequence that lies in, or I'm also going to pick a term that lies in that ball. And of course, since we're shrinking the size of the ball, it follows that the sequence will eventually converge to x as n tends to infinity. Although, I mean, it might never be equal to x, because, I mean, if it's equal to x, then of course we know that, I mean, in this case, it might not be possible. We need to make sure it's not equal to x because of the fact that we're not sure that the boundary of S is a subset of S. So x might not be an element of S. It is an element of S interior. It might not be an element of S. Okay, and we're done with this part. Now we only need to prove this identity in the opposite direction. I'm just going to copy it down over here. So let's prove this in the opposite direction now. So we prove this, and now I'm going to prove it in the opposite direction. So now what I'm going to do is assume, or in fact, you know what? I guess I might just I'm going to run an argument by contradiction. So what I'm going to say is assume, or I'm going to prove by contrapositive. So I'm going to use the contrapositive. And so essentially what I'm going to prove is that if the vector x is not in the interior of S, then for every sequence A of n that, well, it's a subset of S. This is my bad. A sequence is essentially a set. So it's a subset of S such that, well, I'm going to say that A of n, for every sequence A of n of n does not converge to vector x. Okay, I'm just gonna correct this piece real quick. This should be a subset, and finally I believe this should also be a subset. Oh, did I put it? Okay, there's nothing over here. Okay, so I mean, I am probably just going to also run an argument by contradiction after this. And what I'm going to say is assume that vector x is not in the closure of S. Okay. Also, assume by contradiction that there exists a sequence A of n which is a subset of S such that as n tends to infinity, A of n tends to vector x. And I'm going to show that this leads to a contradiction. Moreover, if this is the case, then for every epsilon greater than 0, there must exist a n and not in the set of natural numbers, such that for every n in the set of natural numbers, if n is greater than or equal to n naught, then A of n negative vector x is less than epsilon. So essentially this is just the definition of what it means for a sequence to converge, and in this case the sequence is A of n and it converges to the vector x. Okay, now here's the idea. I'm going to show that this is never possible, or in essence this is never possible to do. And the reason why this will never be possible is because of the fact that x is actually not in the interior of S. And this is where the idea is. But before I do that, what I want to do is I want to rewrite this in some other way. So if A of n minus vector x is less than epsilon, this essentially just means that A of n is an element of the ball centered at x with radius epsilon. And this is true for every epsilon. But here is the issue. This is also a subset of S. So we know that A of n has to be an element of the ball centered at vector x with the radius epsilon, and it also has to be an element of S at the same time. I'm going to show you that this is not possible. Moreover, note, as x is not in the closure of x, this is what we know. There exists an epsilon greater than 0 such that the ball centered at vector x with radius epsilon intersection with S, or you could say with the boundary of S, or you could just say S, it does not matter, is equal to the empty set. So what we know now, since it's not in the closure of S, we know that there exists an open ball centered at vector x with radius epsilon such that its intersection with set S is equal to the empty set. And this is where the issue comes in. For this epsilon, I use this epsilon I use this epsilon. So let's just label this 2 in this case, in 2. I'm going to label this actually epsilon prime just to make sure it's different. Then there exists an n naught in the set of natural numbers such that for every n in the set of natural numbers, if n is greater than or equal to n naught, then a of n is in the ball centered at vector x, comma epsilon prime. However, as a of n, or well, as a, okay, I'm just going to, okay, I just want to be rigorous over here. So I'm going to say take n naught to be a value, which satisfies, I'm going to label this 3, satisfies 3. Let n be in the set of natural numbers. Assume n is greater than or equal to n naught. Then, and this is where the contradiction will come in, a of n is an element of the ball centered at vector x, comma epsilon prime, and as a of n is a sequence in S, what we also know is that a of n is also in S, because the entire sequence a of n is supposed to lie in S. However, as the ball centered at vector x, comma epsilon prime intersection with S is equal to the empty set, a of n cannot lie in both the ball centered at vector x, comma epsilon prime and S. Thus, we have a contradiction, and this completes the proof. So it must be the case that that if such a sequence exists, then X must be in the closure of S. It cannot be outside S. So yep, those are the 2 proofs. I know that this has been a long video. I wasn't able to make a video for quite a long time. So what I just wanted to do is get rid of these lemmas. I initially planned to do 3 separate videos for this, but just wanted to, get done with these lemmas so that we can actually move to the major theorem, the Bolzano-Weierstrass theorem. Just to quickly summarize the first part, there were 2 theorems that we proved. The first one was the fact that every bounded sequence in R has a convergent subsequence. We proved that by using the nested interval theorem and then constructing a subsequence which is based on the nested interval theorem. We ended up using the nested interval theorem to prove that this theorem is true, or the consequence of the nested interval theorem. The third proof was a little bit more interesting in the sense that there were some new concepts over here that I have not previously presented on YouTube. So we wanted to prove that a vector x is in the closure of a set S if and only if there exists a sequence in S which converges to X. So it's easier to prove this in the forward direction by assuming that vector x is in S interior. Is in the boundary of S. It's pretty easy to prove that that there exists a sequence S of n such that in S which converges to X in this case. So if x was an element in S interior, we simply pick our sequence to be X everywhere. And if it's on the boundary of S, we essentially pick balls centered at vector x with a radius that we are shrinking. And then on each step, we pick a term of our sequence that lies in a particular ball. And then as we shrink that ball, it shrinks to X. And we know that A of n, our sequence, also converges to X. To prove it in the opposite direction, we essentially use the fact that if X is not in S interior, or what we wanted to prove is that if X is not in S interior, then there does not exist any sequences of n in S which converges to X. We essentially ran an argument by contrapositive and contradiction. So we assume that X is not an element in S interior, and we assume that by contradiction that there exists a sequence which converges to X. We showed that if this was the case, then there had to be at least one value of A of n, in fact infinitely many, that lied in the ball centered at vector x with radius epsilon. But since for a particular epsilon, we know that the ball centered at vector x comma epsilon is actually not a subset of S. So there has to exist, or they have to exist infinitely many A's of N's, such that all of them have to lie in the ball centered at vector x comma epsilon, and they also have to lie in the set S. But since the intersection of S and the ball centered at vector x comma epsilon is empty, we know that it is not possible for such A's of N's to exist. And we have a contradiction. We know then that X must be an element of the closure of S. So yep, that completes the proof. In the next video, I'm going to present the proof of the Bolzano-Weierstrass theorem. And eventually, okay, so there are three proofs left. There's the Bolzano-Weierstrass theorem. There's a theorem that says that continuous functions map compact sets to compact sets. And then lastly, I'm going to prove the extreme value theorem, and that will complete this series. So yep, I hope you enjoyed the video. If you have any questions, let me know down below. And yep, I'll see you in the next video.